In our last section, we learned about Newton's laws, his three laws of motion, a law of inertia, a law of force, or at least that gives to force, and the law of action-reaction pairs. But we didn't talk about much of how to use these three laws of motion, and that's really what this lecture is about. What we're going to be bringing up is free body diagrams. So these three laws of motion say, first of all, this third law says how to put forces on an object, but the second law says if you can figure out what forces are working on an object, you can find things about the acceleration. And if you know about acceleration, now all of a sudden you can do kinematics if you choose to. So what we're going to be doing in this section is looking particularly about how to apply Newton's second law of motion to things called free body diagrams. And colloquially through the term, when I talk about a Newton 2 problem, this is what I'm talking about, because really what this is an application of Newton's second law. So as we get going, we can look a little bit at the notes that are already posted, and we see, for example, when working with a free body diagram, what we are going to be doing is looking at all forces that act on a particular mass. Eventually, we could have multiple masses, and those different masses are going to have different forces that are working on them. So we'll have to work with each of them independently. From this equational look, this Newton's second law look at forces applied to a particular mass, we can create systems of equations, just like we did with the projectile motion problems, right? We had a horizontal problem and we had a vertical problem, and they were linked through the time. So we could figure out what was going on in each of these diagrams, and we could relate parameters like range and height through the time the projectile was in the air, for example, or how long it took for the projectile to get to a certain part of its trajectory. And the same is going to be true here. It turns out we can have different components of forces, and these different components of forces are going to lead and contribute differently to different parts of the diagram. So then we get systems of equations that can be solved. Now, one of the ways that we are going to commonly apply forces is with ropes or strings or the like. So the tension in some string is going to be a constant. This tension is commonly going to be a way for us to link different masses together. So we might have mass 1 and mass 2 tied together in some way or another. And mass 1 has all kinds of free body diagram stuff, forces that lead to accelerations and everything else. But mass 2 has all kinds of forces and whatnot acting on it as well. And so how do we link what's going on in this mass and what's going on in this mass? It's through the tension. And the tension in that string that connects them is something that's constant. So let's look at some case of me dragging along some block here. What does the free body diagram of a system like this look like? And it turns out there are three objects in this diagram that I've put together, I suppose, for lack of a better word. There's the block, there's me, and there's the rope. And not all of these things are feeling the same forces. They may be feeling the same force magnitudes, but they're not feeling the same forces. So if I was to specialize and look at the block by itself, I see that the block is probably sitting on the floor, so the floor is putting some force on it. That force is a normal force. The block has some mass, so it has an attraction towards the earth. It has some weight. But there's a string tied to it, and the string probably has some tension. How big is the tension? I don't know. That's probably something that I need to find. But these are the three forces that are acting on the block. Now it turns out I'm in this diagram as well. So what are the forces that are acting on me? Well, I'm also standing on the floor. So is the floor putting the same force on me as it is on the block? Probably not. Probably not. But it is going to be some normal force. Is the weight of me the same as the weight of the block? Probably not. But because I have mass, I certainly have a weight. And I have the string tied to me as well. So there's the tension that the rope puts on me. There is the tension that the rope puts on the block. But it turns out that obviously here, those two tensions are described differently. And that's because the last object in this diagram is the rope. And for the rope, there is some tension that I am putting on the rope. There is some tension that the block is putting on the rope. Now, if this is a massless rope, even though T me, which is a vector to the right, and T block, which is a left vector to the left, maybe it has some acceleration. That's totally fine. But if it is a massless rope, T me minus T block is equal to 0, which means that the force that's put on me, the force that's put on the block, those are related to each other. They have some uniform tension. Now, this is the way that we very commonly just leave the problem. Now, if we don't have a massless rope, obviously the tension is not something constant, and it's going to be something that's essentially constant, because ropes and strings and whatnot are typically pretty light, it's certainly compared to some big masses or whatnot. So very often, if the rope is considered to be massless, the tension in that rope is a constant. And we can use this tension now to link things that are happening in the diagram. So in this problem, what I have is me pulling this block. And the block has a mass, and I have a mass, and this is a string that connects it. So there's going to be a tension here and a tension here. I pull on the block with tension T. The block pulls on me with tension T. And that's where it shows up in the different free body diagrams. Okay? As long as the rope doesn't break. Now, we also have a fair amount of flexibility when working with free body diagrams. Let's say I had a bunch of masses hung from the ceiling, and each of these masses hangs from its own string, which means that while we have 1, 2, 3 masses listed here, we have 1, 2, 3 different and unique strings as well, which tells us that there's a possibility of 1, 2, 3 different tensions in each of these strings. And maybe I was to look at a problem like this, and maybe all of these masses, M1, M2, and M3, are the same. One thing that we could look at is, if all of these masses are the same, are all of these tensions the same? And for us to determine this, we actually have to look at the free body diagram. Now, initially, these masses are just hanging from the ceiling. Not a big deal at all. But let's say we were to look at the free body diagrams for each of these masses independently. And that's what we see listed here. For mass M1, it has some weight, right? So M1G is a force that's down, but there's a string tied to the top of it, T1. So this is the free body diagram for mass M1. Now for mass M2, it's a little bit different. There's a string on the bottom and there's a string on top, T2 and T1. But M2 also has some weight, M2G. So its free body diagram is slightly different. However, looking at mass 3 has a string below it, it has a string above it, it has some weight. The free body diagram for mass 3 looks a lot like the free body diagram for mass 2. Not exactly the same because it's a different mass and we have different strings, but the way it's constructed is very, very similar. Now each of these masses is just hanging from the ceiling, so there's no acceleration for any of them. But I don't know what T1, T2, and T3 are. These three things are all unknown in my problem. But because I have three diagrams, 1, 2, 3, and I have three unknowns, I can come up with three different equations found linearly independently. I can solve for T1, T2, and T3 uniquely. There's only one T1, there's only one T2, and there's only one T3. So let's look at M1 first. I see that there is a force up, T1. I see that there is a force down, M1G. Because these are two different directions, they have to have opposite signs. Now, once I know all of the forces are all the things that go on the left of Newton's second law. Net force is equal to, now we need to figure out what goes on the right side, MA. This mass is the mass in your free body diagram, always. So what we see from this diagram is that T1 up, m1g down, so T1 minus m1g is equal to m1a. If there's no acceleration, it's just hanging there, then this is equal to 0. And I can do some solving then, right? I see that T1 is going to be equal to m1g. So now I know what T1 is. Going to the next diagram, I look and see that there's T2 up and there's T1 down. I see m2g down. So these are all of the forces, T2, T1, m2g, with their respective signs. This is going to be equal to the mass in this diagram, which is m2, times the acceleration in this diagram, which is 0. So even though we have m2a here, this is equal to 0, not because m2 is 0, but because the acceleration is equal to 0. In the previous step, we found that T1 is equal to m1g, so I know m1g here, m2g here, 0. I could find what T2 is, uniquely. Now moving on to T3, I see that T3, mass 3, we have T3 up, good, T2 down, good, m3g down, good. This is going to be equal to the mass in this diagram, which is m3, times the acceleration of this diagram, 0. Now putting all these things together, I found T1, and T1 allowed me a way to find T2. Now I know T2, I could plug that in here, and I can find the value for T3. And by solving this system of equations in the way that's described here, if all of the masses are the same, T1 is going to be mg, T2 is going to be 2mg, and T3 is going to be 3mg. The tensions are not the same, even though the masses are. And we use this cascading set of linked equations that we're trying to solve, systems of equations to solve, to figure out what those tensions were. Now let's say we didn't want to know all of the tensions. We only needed to know one of them. There is no reason that we can't be clever with the creation of our free body diagram. So that's what I'm trying to illustrate here. Free body diagrams can contain as many masses or as few masses as you want. What I've done here, because I wanted to find out what tension T2 is, and I don't care what tension T1 is, and I don't care what tension T3 is, I can create a free body diagram like this. And from this free body diagram, I see how much mass is on the inside. It's m1 plus m2. Great. Okay, so what kind of forces are being felt? Well, m1 and m2 together have some weight. m1 plus m2 quantity times g. This free body diagram has a string that's coming out of it, T2. So if I look at the free body diagram that's constructed here, it's the same masses. But now I see this simplified set. I see a force T2 up. I see a force quantity m1 plus m2, g down. This is going to be equal to the mass in the free body diagram, which is m1 plus m2, times the acceleration of the diagram, which in this case is 0. So rearranging terms, T2 is going to be the quantity m1 plus m2, g. And I didn't need to know T1, and I don't need to eventually find out what T3 is. I can do it in one step, if I want to, with the creative application of a free body diagram of my choosing. You'll notice it's the same answer that I found with the other technique. Now, in each of these free body diagrams, the acceleration was equal to 0 because the blocks were hanging from the ceiling. What happens if the acceleration was not equal to 0? Maybe we were in some elevator that was accelerating upward. Okay, well now the tensions are going to be a little bit different. What's different about the free body diagrams? Now we have a T1 up and M1G down. These are the forces in order to find the net force up and down. But the net forces are going to be equal to the mass of the diagram times the acceleration. Because this acceleration is up or in the direction of T1, that's how the signs are going to work. And we'll notice now that T1 is not equal to M1G. It's equal to M1 times the quantity A plus G. If you tell me what the acceleration is, then I can tell you what the tension is. But the tension is not M1G anymore because there's an acceleration in our problem. And if we knew what the tension was, we could calculate the acceleration. And we do the same sort of techniques for mass 2, same sort of techniques for mass 3, and if we wished, we could solve them all. And we find out different applications of what those tensions are going to be. So what I'm trying to illustrate here, by applying Newton's second law to free body diagrams, is we put all of the forces, up and down, right and left, whatever, on the left side of the equation. That will be equal to the mass that's in the diagram times the acceleration of the diagram. Forces equal mass times acceleration. Okay? So when I ask you for a Newton 2 expression, you can't be mixing those things. On the right-hand side, we had an MA. Is MA a force? No, MA is not a force. The forces are on the other side of the diagram. That acceleration is due to all of those forces. I need to know all of them to figure out what A is. MA is not a force. So yeah, over on this side, we could have things like weight. We could have things like normal force. We could have things like tension. There's a variety of ways that we could have forces coming about. When we know all of those, that's equal to mass times acceleration. That is Newton's second law. So when I ask for a Newton 2 expression, and I see MAs over here, or I see other weird forces like tensions over here, that tells me you don't know what Newton's second law is. That is wrong. Even if it's mathematically consistent, it's wrong because forces show up over here, masses and accelerations show up over here. Okay? They're not the same thing. So something to keep in mind. And we can be clever about what our free body diagram is. But when we are being clever, we need to be careful to make sure that we really do contain the mass of our free body diagram. That we really are looking at all of the forces that are applied to this block that we have cordoned off as our free body diagram. That's very important. Okay? Another thing that we might want to keep track of is, well, what if we had some blocks that were on some inclined plane? How do we resolve what's going on? And for that, I'm going to go here to the paper. So let's say we had some ramp, some inclined plane here of some kind. My pen is dying, probably running out of ink or something. Okay, let me just pick a different pen, that's easy. Okay. So I'm going to have this inclined plane. I'm going to have a block on the inclined plane. Okay? Now, let's say I wanted to figure out what kind of acceleration we get for this block of mass m going down the inclined plane. If this is some angle theta, well, if I wanted to, I could come up with components of forces. I have some components of acceleration. I could really do this as a horizontal and a vertical problem if I wanted to, right? So for example, I see that there is going to be some normal force. I see that there is going to be some weight, mg, and maybe we've got, actually, let's go here in the notes. I've actually got something very similar. Let's do a setup from the notes here first. Let's go here. So this is a problem. We've got a skier of a particular mass being pulled up a snow-covered slope, okay, at a constant speed by a tow rope that is parallel to the ground. The ground slopes upward at a constant angle of 26 degrees, but we are asked to find the tension in the rope, and if we wanted to, we could find the normal force applied to the block. So I'm going to sketch this problem here first. And by block, I mean the skier. So it's just some mass, so to speak. So here I've set this up. And you already saw a little bit on that page that we know a couple of these forces. So there is the normal force, which is this way. It's being pulled by a rope this way. We have some weight of this skier, right? And we need to figure out maybe what horizontal and vertical components of this are. Let's say we really want to do this problem horizontal and vertical. We really are handling it this way. So for that, we need to do a little bit of trigonometry. And we might say that this is angle theta. That's pretty easy to see. And with respect to here, this is angle theta. That's pretty easy to see. And from here, this is angle theta. Just using a little trigonometry. As this slope gets bigger, we get these different sort of impacted sort of things. And we are going to have, let's see, in this problem, is the dude accelerating? The dude is not accelerating. Okay, good. So the acceleration is equal to 0. If I'm doing this as a horizontal and vertical problem, I might want to look at what are the x components of forces. And I see t cosine of theta to the right. I see n sine theta to the left, so n sine theta. Do I see any other components of force to the right or to the left? I have a weight force, but the weight force is only down. Okay. So this is equal to 0. These are the x components of force. What about the y components of force? Here, what I see is a normal force up of n sine theta, n cosine, sorry. N cosine theta. The tension force, t sine theta up, t sine theta, and I see a weight that's down. There is no acceleration. Now normally this would have been m times a, normally this would have been m times a, but there is no acceleration. He's going up at a constant velocity. Now there's two things that we don't know. I don't know the normal force. If I did know the normal force, I could find the tension. Over here, I don't know the normal force. If I knew the normal force, I could find the tension. What I have is two equations with two unknowns. I don't know tension, I don't know normal force. I don't know normal force, I don't know tension, but I know everything else. So let's say I wanted to try to find out what the tension and normal force were. From this equation, we see that t cosine theta is equal to n sine theta, or that t is equal to n sine theta over cosine theta, which is tan theta. Now, I don't know what the normal force is, so I can't find the tension, but I can take this tension and plug it in over here. And here we see that n cosine theta plus tangent, which is tension, and tangent of theta, sine of theta, this is equal to mg. I'm just moving that mg over to the other side. Now I can factor an n cosine theta out over here. And here I would have a 1 plus n tangent theta sine theta over cosine theta. Sine theta over cosine theta is tangent theta. So this is tangent squared theta is equal to mg. what is 1 minus tangent squared? Okay, so once again, sine squared theta plus cosine squared theta is equal to 1. If I divide both sides by cosine squared theta, this becomes tangent squared theta plus 1 is equal to 1 over cosine squared theta. So 1, and this is supposed to be plus, sorry. We see that there's a plus sign there. 1 plus tangent squared is 1 over cosine squared. So n cosine theta over cosine squared theta equals mg, or normal force is equal to mg cosine theta. Now I do know m, I do know g, I do know theta, so I know the normal force. This is a number that I could actually calculate. And plugging this normal force in over here, the tension is mg cosine theta times tangent theta, but tangent theta is sine over cosine. So the tension is mg sine theta. Okay, so we could calculate what the tension, what the normal force is. We could do the problem as proposed. But I'd like to highlight something different. The reason why we had to know a lot of trigonometry here is because we weren't clever with how we constructed and dealt with the different forces. What if we were to do the exact same problem, but we were to reorient things? So we're going to have this same slope, same ramp here. We're going to have the same block, same angle theta. We're going to have the same forces. We're going to have tension. We're going to have normal force. We're going to have weight. So these are the same forces that we had before. Only instead of having a coordinate system that's set up horizontally and vertically, I'm going to set up a coordinate system where this is the x direction and this is the y direction. I have rotated my coordinate system. Now what are we going to get for our equations? So let's do the x equations first. Now in the x direction, I have a t. In the normal force doesn't contribute in the x direction, but I do have a component of the weight. It turns out it's going to be mg sine theta, and it's going to be down the ramp. So we've got this force plus this force, down, down. That's the same thing as mg. So t minus mg sine theta is equal to m times the acceleration, but there's no acceleration, is equal to 0. Now we do the y equations. What's going on in the y direction? Well, I've got a normal force that's up. I've got an mg cosine theta down. That's equal to 0. So the normal force is mg cosine theta. The tension is mg sine theta. How does this compare with what we saw before? Tension is mg sine theta, mg sine theta. Normal force, mg cosine theta, mg cosine theta. Which is easier? I think we would all agree that this seems to be a complicated mess because of a poor choice of coordinate system. This is much easier because of a good choice of coordinate system. And we get to choose. The choice of coordinate system doesn't matter. We get to choose which coordinate system we want, but we want to choose the correct one if we are given some choice. That's something for us to keep in mind. Okay. Now one thing that's hard to figure out for a lot of students going from book to book is figuring out which of these angles, let me pull this up here, on this free body diagram for this mass, or for this mass here, how do I figure out what angle is what? So here we've got this big inclined plane. Okay. We've got this mass on the inclined plane. Maybe we have this angle theta. And we're trying to figure out, given this mass, mg, I need to come up with a right triangle. Mg is always going to be the hypotenuse of this right triangle. So what other triangle are we trying to make? The way we create this rotated coordinate system like this, is we have to draw lines along the coordinate directions. So I draw some line parallel to y. I draw some line parallel to x. That makes this a right triangle. But then we have to figure out, well, which of these angles is theta? I'm not exactly sure. Now, I happen to know that this is angle theta, but how would we convince ourselves of this? And for that, I'd like to go to Mathematica just for a moment. So here what I have is some block on an inclined plane. This block has a certain weight, 2 newtons. Okay? Now this inclined plane has an adjustable theta. Here's a large value of theta, small value of theta, which says that this corner is what we're talking about with theta. Now over here, I not only have the weight hypotenuse, but I have components created as well. I have a component that is perpendicular to the plane, and I have a component that's parallel to the plane. And you see that for any angle theta, blue is always perpendicular, green is always parallel, right? So this blue, green, red relationship creates a right triangle. This is the right angle in the right triangle. So to figure out which angle is which, I see that this angle is small, this angle is large, just like this angle is small and this angle is large. If theta gets bigger, this angle gets bigger, just like this angle gets bigger. This angle is getting smaller, just like this angle is getting smaller. This angle is getting big, just like this angle gets big. This angle gets small, just like this angle gets small. Now for any of these arrangements, we see that the red never changes. The hypotenuse is the hypotenuse, the weight is the weight doesn't know anything about your ramp. It can't change. But based upon the ramp, we can have different components. Adding blue to green is always going to give us red. So what we're hopefully getting a little bit more intuition about is if this is some angle theta, this angle up here is the same angle theta if our right triangle has this, parallel component here, this perpendicular component there. Or in the case of our piece of paper here, the triangle's turned around, but this angle corresponds to what's happening up in here. That's what makes this the adjacent side for cosine. That's what makes this the opposite side for sine. That's why we got those things. Okay? So through the course of this, we've gotten a little bit of intuition. First of all, how to make free body diagrams. Where do we put the forces? Where do we put the accelerations and the mass? We can be clever with our choice of free body diagram. We can include one mass. We can include as many masses as we want. We can link a bunch of masses together if we choose to. Perfectly and totally fine. Maybe we could work with ramps and break forces up into components and be creative with how we construct a coordinate system in order to make problems a little bit easier. But now for the remainder of this little video, I'd like to actually look at a couple of problems. And the first one I'm going to look at is, let's say we just have a plane. We have a block sitting on the plane. This block has a mass m, and I'm going to put a force on it at some angle theta with respect to the horizontal. And I would like to find what is the normal force applied by the floor and what is the acceleration of the block to the right. Those are the two things that we are going to look for. Now, looking at this, I want to figure out what forces are at play. One of the forces was actually given to us, but not all of the forces were given to us. Two forces are missing. One of them, the normal force, one of them, the weight. Now with this, we know all the forces that are at play. This one, and this one. These are all the forces. What is a convenient choice of coordinate system? Well, I look at this and I see that the acceleration we're asked for later is going to be to the right. Why don't I come up with some configuration where I don't find components of acceleration? Just like I did with the ramp. Just like I did with projectile motion problems. I didn't look at components of acceleration. I only looked at acceleration by itself. So I'm going to do components of force and not components of acceleration. I'm doing this. Okay. Now looking at this, what forces do I have to the right and to the left? The force to the right is F cosine theta. Do I have any other forces to the right? Nope. So because of that, force to the right has to equal to mass times acceleration to the right. And we're told that all of the acceleration is in the x direction, so this is ma. What about what's going on with the vertical problem? Now we have a couple of forces. I have a normal force that's up. I have a weight force that's down. Is that it? No. I have a vertical component of this force as well. We don't have any acceleration up or down. So even though this is may, the acceleration in the y direction is equal to 0. So from these two equations, we can answer these two questions. So what is the normal force applied by the floor? Normal force is mg minus f sine theta. If there was no string applying force in the way that was pictured, the normal force would be equal to mg. But this is another application saying that normal force is not equal to mg. The floor and the block have a force pair, but the block force is not mg. The force pair of the block is with the Earth, the gravitational attraction to the Earth. The normal force does not have to be mg. The normal force and the block are a force pair, but it's not because of mg, it's because of all of the forces that are on the block. So somebody pulling up on it is going to lower the normal force. It's not just the floor that's pushing up. The person and the floor are pushing up, altering the normal force required by the floor. But we also see over here that if we want to define the acceleration is going to be f over m cosine theta. So yeah, we can find the acceleration, and maybe in some problem, maybe we're told that the mass is 10 kilograms. Great. Maybe angle theta is 40 degrees. Great. Maybe we're told that the force that's applied is 20 newtons. Okay, so in this problem, I know F, I know M, and I know theta. In this problem, I know M, I know G, I know F, and I know theta. I could actually calculate numbers for both of these things if I wished. So let's bring up a calculator. Let's do the acceleration. Actually, the normal force was the first thing that was asked for us. So sine theta is going to be 40 sine times the force, which is 20. And this is subtracted from m times g, which is 10 times 9.8. Normal force is 85 newtons. Now normally, if g is just about 10, the normal force with nobody pulling on it would have been close to 100. We see that the normal force is smaller because of this f sine theta. What kind of accelerations are we going to have? F over m, 20 divided by 10 is just 2. 2 times the cosine of theta. 1.53 meters per second squared. So we can calculate accelerations, we can calculate normal forces. This is a problem that we could do for the simple case of two blocks. We could also look at the case of the problem that's shown here. So here in this problem, we have an 8 kilogram block of ice released from rest at the top of a 1.5 meter long frictionless ramp that slides downhill, and at the bottom of the ramp, it reaches a speed of 2.5 meters per second. We would like to find the angle between the ramp and the horizontal. Now, there's part of the problem that's crossed out because the way that he handles frictional force in this book is a little bit weird. We don't handle frictional forces that way. We're going to do that in our next discussion on friction, next part of the lecture. But we're going to do part A of this problem. And so to do this, we're going to have some inclined plane, as shown here. We're going to have some block mass M. Okay. Now this block of mass M feels a normal force because of the ramp. This block of mass M has some weight. What other forces are at play? So there's no friction because it's on ice. There's no strings tied to it or anything like that. We are eventually going to get an acceleration down the plane, but acceleration is not a force. This is everything that's applied. Now, just for clarity later, our ramp is said to be a certain distance long. This is the distance that was given to us. I'm just going to call it d. And we are asked to find this angle theta, the angle that the block makes with the inclined plane. Now the block is going to slide this distance d, and at the bottom of the ramp it's going to be moving at some velocity. These are some of the things that we know. But before we get there, how could we find an expression for the acceleration of this block? Well, we have two sets of equations that we could look at. We could have a coordinate system where this is the x direction, coordinate system where this is the y direction, and now in the x direction, I'm going to have an mg sine theta. Sorry, mg sine theta, but that's the only component of force that's down the plane. So that's equal to ma. If we wanted to, we could find the y components of forces. So the y component, we're going to have an n minus mg cosine of theta. There is no component of acceleration in that direction, so this is equal to 0. So if we cared about the normal force would be mg cosine of theta, just like before. Over here, we see that the acceleration is going to be equal to g sine theta. And if we knew what the angle was, we could find the acceleration. If we knew what the acceleration was, we could find the angle. And it turns out that we're looking for the angle. We're trying to figure out what's going on with this expression. But I need to find the acceleration. Now what we're told in the problem, that as this block accelerates down the plane, it will reach some final velocity at the bottom. We need to use a kinematic equation. So what are our kinematic equations? We know that v final is equal to v initial plus at. We know that x final is equal to x initial plus 1/2 v initial plus v final t. We know that x final equals x initial plus v initial t plus 1/2 a t squared. And we know that v final squared is equal to v initial squared plus 2a x final minus x initial. Now each of these first three equations, we need to know something about the time. And I don't know how long it takes to get to the bottom of the ramp. I do know how long the ramp is. I do know what the speed is at the bottom. I can use this kinematic equation to find the acceleration, or an expression of the acceleration. So what's our final velocity? We'll just call that v. What's our initial velocity? It started at rest. What is our final position? D. What was our initial position? 0. So we see that v squared is equal to 2ad, or that the acceleration is v squared over 2d. So I have two expressions for acceleration, here and here. They're the same acceleration. So why don't I just set them equal to each other, saying that g sine theta is equal to v squared over 2d. This means that sine theta is v squared over 2gd, or that theta is equal to the inverse sine of v squared over 2gd. We know the final velocity, we know g, we know d. We can solve for this angle. We can find it. Now in this problem, we see that d is 1.5 and v is 2.5. Okay, pulling up our calculator here, v squared, which is, let me just check here, v squared is 2.5 squared divide by 2, divide by 9.8, divide by 1.5, inverse sine, 12.3 degrees. That was the slope that had to be made. So yeah, we can do a problem like this. So we have this block on an inclined plane. We have a block that was just on a regular tabletop. Wonderful, wonderful. But this has all been instances where we only had one block. What if we wanted to look at a different situation, something called the Atwood's machine? What's going on with Atwood's machine? Atwood's machine is a system where we have two blocks connected by a string that's hung over a pulley. Why is it called Atwood's machine? I have no idea off the top of my head. But now we have two masses connected by some string. We're linking now free body diagrams that can be created. Now, we've probably played with masses on strings over a pulley before. If I pull M2 down, M1 is going to go up. If I pull M1 down, M2 is going to go up. That happens because the length of the string is fixed. So if we were looking at some case where I'm pulling M1 down, giving it some acceleration, M2 is going to go up with exactly that same acceleration as long as the string doesn't break. One of these free body diagrams is associated with mass 1. And mass 1 has some weight, M1g, and it's connected to a string, so it has some tension applied to the top. M2 has some mass, so it has some weight, M2g, it's down. It is also tied to a string at the top, T. These two strings are the same string, so they have the same tensions. But over here, M1 is being accelerated down, which makes M2 accelerated up. Looking at these two free body diagrams, T1 is up, M1g is down, T1 is up, M1g is down, but the acceleration being a vector quantity is down, making the right-hand side minus M1a. On the right diagram, we have a tension up, positive, M2g down, negative, but the acceleration is up, meaning our mass times acceleration is M2 times a. This is our two equations that came from these two diagrams, and it allows us to find two things that we might have not known. What is the acceleration in the system, and what is the tension in the string? So we can actually use these equations. I can solve for t in equation 1, plug it into equation 2, plug it in. So we see over here, t is equal to m1g minus m1a. Plug that in down here for equation 2. Minus m2g is equal to m2a. The only thing I don't know in this equation is the acceleration. I solve, I find the acceleration. Plugging this acceleration into equation 1, I find out what the tension is. Great. Now there's a couple things that we see. If m1 is bigger than m2, the acceleration is positive. The way that we pictured this is fine. If m2 is bigger than m1, the acceleration is negative. Is that a problem? Not really. If m2 is bigger than m1, I expect m2 to fall and m1 to go up. So it really works the way that it's supposed to. We just had to guess on what the direction of acceleration was going to be in order to create a consistent set of equations. We don't have to know what m1 and m2 are off the bat, but once we know what m1 and m2 are, we can find out the acceleration, whether it's positive, whether it's negative. Is it possible for us to get a negative tension? No. Whether m1 is bigger or m2 is bigger, it doesn't make any difference. The tension is going to be the tension. And in limiting cases, we could look at limiting sorts of behavior. What happens if m1 is very, very large, like a shot put, and m2 is very, very small, like a ping pong ball? Well, obviously, if m1 is much, much bigger than m2, I expect m1 to fall and m2 to go up. But what do we see for the acceleration? M1 is very, very large, m2 is very, very small. So I look at this expression for acceleration, m1 is maybe 1,000, and m2 is 1. Well, 1,000 minus 1 is essentially 1,000. On the bottom, m1 plus m2, 1,000 plus 1 is essentially 1,000. this ratio essentially becomes 1. The acceleration in the system is essentially a g. The shot put doesn't know that the ping pong ball is attached to it. It shows up in the math. It shows up in the math. Similarly, what's the tension going to be? Well, if M1 and M2 are very, very different, M1 times M2, 1,000 times 1 is essentially 1,000. Right? Okay, so M1 plus M2, that's basically 1,001, So we have a couple of units that are associated with it, but the tension really does have different kinds of units. So M1 and M1, this on the bottom, M1 plus M2 is essentially M1. So 2 M2G, that's a pretty small tension. That's a pretty small tension, as you might expect. So in limiting behaviors, we can get some sense of whether our equations make sense. But one last problem that we could look at, if we wanted to, is to look at an applied case of this Atwood's machine. So what if we had an Atwood machine, and I had M1 here, I had M2 here. We're going to start with M2 sitting on a tabletop. And M1 is a distance h above the table. Now I'm also, in addition, going to apply one more force. I'm coding it in. I am going to pull down on M1 with some force F. I'm really going to put that on here. And now from this, let's say we know a couple of things. M1 is going to be 2.5 kilograms. And M2 is going to be 2 kilograms. And the force that I'm applying up there is 4 newtons. And finally, that distance that M1 starts above the table is going to be 80 centimeters, just short of a meter. And I would like to find a couple of things. How long does it take for M1 to hit the table? Also, how fast, is M1 moving when it hits the table? Okay, so the first thing we need to do is create some free body diagrams. One of the forces I know, but that's not the only one. M1 also has a weight, M1G. M1 is also connected to a string that applies a tension. M2 has some weight, M2G. Now I'm going to basically say that the normal force is equal to 0, so M2 is just touching barely the table before I release it and it takes off. So the other force that's at play here is the same string that was attached to M1 is also attached to M2. These two diagrams give me two equations. One of the equations, now first of all, M1 is going to fall, right? So M1 is going to accelerate this way, and if M1 falls, M2 accelerates up. So this M1 diagram says that force plus M1G minus T is equal to M1A. And you're thinking to yourself, hold on a second. When we were looking at these before, Forces that were up were positive, forces that were down were negative, accelerations that were up were positive, accelerations down are negative. All I did was factor out a minus sign. This is perfectly and totally fine. This force, if it's positive, and this force, if it's positive, are in the direction of positive acceleration. Acceleration is this way. So this being positive, and this being positive is consistent with the diagram. The tension is opposite that direction. That's what makes it negative. This is the same thing as minus F minus M1G plus T equals minus M1A. All I did was factor out a minus sign to make it look different. It's the same equation. What happens over here? I have a tension that's in the direction of acceleration, a weight, M2G, that's opposite the direction of acceleration. The mass in this diagram is M2. The acceleration is up. So these are the two equations that I have. I don't know the tension in the string, and I don't know the acceleration. It turns out I'm not asked both of those things. I'm really only asked for the acceleration. So why don't I make this as easy as I could and solve one of these equations for tension, plug the tension into the other equation, and find out what the acceleration is going to be. So over here, I can say that the tension is equal to M2G plus M2A. I can take this tension and plug it in up here, where we find that F plus M1G minus the tension, so minus M2G minus M2A, is equal to M1A. Well, let's take this thing with the A, put it on the other side. We see that M1 plus M2A is equal to F plus M1 minus M2 G. So force, kilogram meters per second squared, is a Newton. Kilogram meter per second squared, these are all consistent units. But the acceleration is F plus M1 minus M2 G divided by M1 plus M2. Newtons divided by kilograms is going to be meters per second squared. So this really is an acceleration. Now, I'm not asked to find the acceleration. What I'm asked to find is how long does it take for M to hit the table? And so again, we might want to go back to some kinematic equations. I know the acceleration because I know the mass, I know the force, I know all that sort of stuff. In fact, if I wanted to find this number, I can. Let's pull up my calculator here. I know that M1 minus M2, so 2.5 minus 2 times 9.8. Okay, so I need to add to that the force, plus 4 is equal to this, divide by the sum of the masses. Divide by 2.5 plus 2. So this is the acceleration, 1.98 meters per second squared. This is the acceleration, but this isn't what we were asked for in the problem. We were asked to find the time that it takes to hit the ground. So we don't know what the final velocity is. If we knew the time, then we could find the final velocity. Great. We don't know initial or final velocity. Actually, we know initial velocity, but we don't know final velocity, so this doesn't help us either. However, we know that maybe it starts at some final height, ends at some final height. It started from rest, and we know what the acceleration is. Using kinematic equation number 3, we could solve what's going on. So what's kinematic equation number 3? Let's look at mass 1. y final equals y initial plus v initial in the yt plus 1/2 a in the y t squared. So my final position in the y is 0. My initial position in the y is h. I don't have any initial speed, but my acceleration in the y is down. At squared. So now I can solve this for time. We know that 1/2 a t squared is equal to h. So time must be 2h over a under square root. So what is the time? Using our calculator, we've already got this acceleration. I can put it in the denominator, times 2, times h, which was 80 centimeters, or 0.8 meters. I take the square root, 0.899, so 899 milliseconds. So a little bit short of a second. Okay. So now I know not only what the acceleration is. We weren't asked for it, but I know it. I know the time that it takes to do this. For part B, with this set of information, I can certainly find out how fast it was going. I could have used this because I want to know the final speed, but I know the acceleration and I know the distance. It's traveling distance h. Similarly, up here, I know the acceleration and I know the time. So I can use kinematic equation number 1 now, if I wanted to. So because v final is equal to v initial plus at, I know a, I know t, I know this is 0. That final velocity is a times t. So I know my time, 1.9, and actually, if we wanted to rearrange terms here, a times t over here, a is this whatever number it is, but t is 2h over a. This is by multiplying by time, it becomes this. So if I know h, I know a. The same thing we would have gotten from here. Final velocity is 2ah under the square root, 2ah over a square root. Interesting. We don't need to use the time, but I could go back and find out what the acceleration is, 1.98 in this particular case. I could get more details if I wanted to, times h, 0.8, times 2, great. Take the square root. So about 1.78 meters per second is how fast it is going when M1 hits the tabletop. Sorry. So this is just to give us some experience and practice working with free body diagrams. We connected masses together. We looked at masses on inclined planes. We looked at masses on tabletops. Masses on tabletops here. We've gotten some practice working with free body diagrams. In the next component of this lecture, we're going to add friction. Friction is something that we have not yet dealt with, but will really just be a small correction to the problems that we analyze.